Okay, I'm back to continue our notes on polynomial functions. We have to get a few vocabulary terms out of the way, so let us begin. A root of a polynomial function is an x value that has a corresponding y value equal to 0. Roots can be real or imaginary, but for our purpose of sketching the graph of a polynomial function, we will only be concerned with real roots. Real roots are the roots that we can actually plot on the x-axis, which is a real number line. An x-intercept is the location of a real root because the y-coordinate of any point on the x-axis is equal to 0. There is a common misconception that a graph must, quote, intersect the x-axis at an x-intercept. Although this is often the case, it is not necessary for the graph to cut through the x-axis in order for the graph to contain a point with a y value of 0. When we know a real root of a polynomial function, we automatically know a factor of that polynomial function. For instance, if x equals 3 is a real root of f of x, then we know that x minus 3 is a factor of f of x. The multiplicity of a real root is the number of times that real root occurs, which is the same thing as the number of times that root's factor repeats. And we'll see examples of this as we go along. But first and foremost, I just wanted everybody to understand that a root of a polynomial function is often called an x-intercept. However, that doesn't mean that the graph actually has to cut through the x-axis to be considered an x-intercept. Any point on the xy axis that has a y value of 0 is going to be considered an x-intercept. It's not an x-intersect, it's x-intercept. Okay, so it's two different words here, but in the past you've always been told that in order to have an x-intercept is where the graph crosses the y-axis, well, or the x-axis. It doesn't have to cross the x-axis, it just has to touch the x-axis. Oftentimes it does go through, but it doesn't have to. All right, let's get into this word multiplicity, because each root of a polynomial function is going to have a particular multiplicity assigned to it, and that's going to describe the behavior of the graph at that particular root. So let's move on here. Multiplicity equals 1. The graph simply cuts through, intersects, or crosses the x-axis with no other special behavior. And this is what you're used to seeing when you have an x-intercept. You're used to seeing the graph cut right through the x-axis. So this should not be new to anybody out there. Okay, I'm going to take this just a little bit further, and we're going to apply our knowledge of the leading coefficient and the degree of the polynomial function to decide whether or not we can write the equation for each of these graphs, or a possible equation for each of these graphs. All right, well, one of the first things I notice about example 1 is that this graph is starting high and ending low. So I'm just going to give myself a little xy axis, and I'm going to say this graph started high and ended low. Because my far end behaviors are opposites of each other, I definitely know that I have an odd degree polynomial function. So n has to be odd. I also know that when I have an odd degree polynomial function like y equals x cubed, that function typically starts low and ends high. The only way I'm going to start high and end low is if I have a vertical reflection or a negative leading coefficient. So I am going to write here that my coefficient, my leading coefficient, has to be negative. Now this tells me a little something about my function. Okay, so let's go through and let's try and write the equation for this graph. I'm going to start with f of x equals, come down here on that f a little, f of x equals, well, I know I have a negative leading coefficient, so why don't we just go ahead and get that out of the way, and we'll start with negative, and I'll just make it a 1. You can make it anything you want, really, when it comes right down to it. But negative 1, if I have x equals negative 7 as one of my roots, then I have to have x plus 7 as one of my factors. And since this graph is simply cutting through the x-axis, the multiplicity of that root is a 1. The multiplicity of the root is the number of times you're going to see that factor occur, so x plus 7 is to the first exponent. I also have a root of negative 1, and if x equals negative 1 is a root, then x plus 1 is a factor. And I'm also going to have a multiplicity of 1 there. See how my exponent just becomes a 1, that's it. I now have an x-intercept of 3, which means x minus 3 has got to be a factor. And it's going to occur one time because 3 has a multiplicity of 1, therefore the factor is going to occur once. So I'm just going to clean this up just a little bit, and I'm just going to say f of x is equal to x, oops, sorry, I lost my negative sign. See how that happens so fast? Because I really didn't like the equal sign either. So negative, I'm going to drop my 1. Just say x plus 7. I'm not going to write the first because if I don't put any exponent, it's presumed to be the first anyway. And those are my 3 factors. Now if I look through this graph here, and I look through my graph and look through my function, and all I do is I add my multiplicities up. I take this first multiplicity here, this, let me change my color here. Very good. So if I have this exponent as a 1, which is the multiplicity on my negative 7, this is the multiplicity on my negative 1, this is the multiplicity on my positive 3. If I add those multiplicities up, I get the number 3, because 1 plus 1 plus 1 is 3. 3 is definitely odd, and I have this negative right outside the front here is my leading coefficient, so I'm good to go, and this stuff kind of checks off for me a little bit. I'm going to go back here, and I'm just going to box this. I'm going to pretend that this was my question, and I'm done. I could continue and ask you more questions about this function, but I think we'll just leave it where it is for right now. Okay, example 2. Again, I'm looking at a multiplicity of 1 at negative 4, at 0, at 2, and at 6. So the first thing I notice here is that I have a polynomial function that is starting low and ending low. Well, when a polynomial function starts and ends with the same behavior, like low, low, or high, high, I know that the degree of my polynomial function has to be even. So I know n is even, just like the function y equals x squared. But y equals x squared starts high and ends high. This one is starting low and ending low, which means I must have another vertical reflection going on. And the only way to do that is to have a leading coefficient, which is negative. So I'm going to write down here my leading coefficient is less than 0 again. It's going to be pretty easy to handle. Okay, let's start off with f of x equals, I'm going to start with that negative 1 again, and I'm going to look at my first root, or 0, whatever you'd like to call them, negative 4. If x equals negative 4 is a root of this polynomial function, which it is, then x plus 4 has got to be a factor. That factor is just going to occur once because this is a multiplicity of 1. X equals 0 is another root, and that only occurs once as well. I think most people like to start off saying like x minus 0 quantity to the first, and that's okay, we can do that. When x equals 2, x minus 2 is a factor, and it's a multiplicity of 1 again. And when x equals 6, x minus 6 is a factor with a multiplicity of 1 again. So let's repeat our process from last time, and let's add these multiplicities up. I have 1, 2, 3, 4. Does that make sense that I would have a multiplicity of 4? Sure does, because I said earlier n was even. And I got this negative hanging on the outside here, so that checks pretty good. And I pretty much know I have the right function here. So I'm going to clean this up a little bit. F of x equals, I'm going to keep the negative, but since this x is all by itself, basically, I'm going to write it first. I know it puts my roots out of order, and that's fine to be out of order. It's nice to maintain order, but when you just have x equals 0 as one of your roots, we typically will factor the x to the outside. And then we have x plus 4. I'm not going to write to the first, but I could. X minus 2 to the first, and x minus 6 to the first. Whoops, I said I'm not going to write those, right? Okay, so I think we're pretty good to go here. Pretty much good to go. And this would be the equation of my f of x. I would most likely make you go a little bit further, but I just want to talk about multiplicities right now, so we're just going to move on. Okay, here we have examples 3 and 4. We're talking about a multiplicity of 2. The graph is tangent to the x-axis. The graph does not cross the x-axis. A point of tangency is when the graph comes down, touches, and moves right back into the same direction it came from. It will not cross. It's like you're running up to a wall, tagging it, and running away. And the x-axis is the wall that you're tagging. Okay, let's come over here and let's start trying to write this function. We have f of x equals, oh, you know what? let's backtrack a little and analyze, okay, you guys? First thing I notice here when I stop to think about it is that this function is starting high and ending high, which means that my degree has to be even because that is the behavior of an even degree polynomial function, starting high and ending high. So is also starting low and ending low, which you'll see in the next example, but for right now, starting high and ending high, just like y equals x squared. And so we are, because we're just like y equals x squared, we know that the degree is even because of the square, but we also know that the leading coefficient is just going to be positive, so greater than 0. Okay, let's go ahead and try and write our function. We have f of x equals, I don't need to worry about that negative sign like I did a few minutes ago because my leading coefficient is positive. I have a negative 6 as one of my roots. So if x equals negative 6 is a root, then x plus 6 has got to be one of the factors. And this has a multiplicity of 2 because I have a point of tangency. This little behavior of the graph right here with this little U shape indicates a point of tangency right here at negative 6. And a point of tangency is described using a 2 for your exponent right here on your factor. Multiplicity is a 2, which means the number of times the factor is going to reoccur is twice. So instead of writing the factor twice, I just put quantity squared, and that kind of makes good sense, I hope. Okay, moving on, we have another root of x equals 4, and if x equals 4 is a root, then x minus 4 has got to be one of your factors. It also represents a point of tangency to the graph. You see that U shape right here? So at x equals 4, I'm going to have a multiplicity of 2. I'm going to come back in here and put a square there. And then that square represents my multiplicity once again. So I have 2 points of tangency on this graph. There's really no way to clean it up, but I will go ahead and just rewrite it and box my answer. F of x is equal to x plus 6 quantity squared, x minus 4 quantity squared. And we will box that. Good to go. Example 4. This function is a little bit different than example 3 because instead of starting high and ending high, we are starting low and ending low. So there's some similarities. At least we have the same foreign behavior, even though instead of high, high, it's low, low. That tells me still that n is even. Even degree polynomial functions do that. Even degree will start and end in the same direction. However, if I'm starting low and ending low, that's kind of like y equals negative x squared. So I realize that my leading coefficient is going to be negative. Okay, let's start writing this function. F of x equals, let's get that negative out of the way. And let's play around with my first root here. My first root happens right here at negative 5. So when x equals negative 5, that tells me that x plus 5 has got to be a root. We're dealing with a multiplicity of 2 because we have a point of tangency, so therefore my factor has an exponent of 2. The multiplicity of the root is the number of times the root occurs. It's also the number of times the factor occurs. So we tell our factor to occur twice by putting a square on it. And now with the next root that we have, which is x equals 0, see this point of tangency right here again? Okay. So I'm going to come back here and I'm going to say x minus 0 quantity squared. It really doesn't matter if you say minus or you say plus. I mean, x plus 0 gives you x minus 0 gives you x. It doesn't matter the sign in the middle. So that's pretty much good. I'm not sure I like that 0 a whole lot, so I think I will just erase it and write it again. That's a little better. And my next 0 or root is going to be a 3. So if x equals 3 is a root of this polynomial function, then x minus 3 has got to be a factor, and we're going to quantity square it again because just like the other 2 roots that we had here, see this upside down u? All right, right there at 3, that shows me that I have a point of tangency, which means my multiplicity is a 2, which means my factor is being squared. Same thing over and over and over again. Let's add these 2's up. 2, 4, 6. Is 6 an even number? Yes, it is. My leading coefficient is negative, and that checks. And I don't see a check mark over here on number 3, which means I didn't add these things up and double check everything. But if I take this 2, this exponent of a 2, and this exponent of a 2, and I add them together, I do indeed get 4. My leading coefficient is positive sitting out front here, so that did check as well. All right, let's go ahead and write this final answer. F of x is equal to, okay, the negative sign is coming first. I'm going to take this right here and just call it x with a square on it, and then x plus 5 squared, and then x minus 3 squared. Good to go. And we are done. I get a lot of people that like to take this negative sign right here, this negative, and try to multiply it through one of the factors. Be careful and don't do that in this case especially, because if you take a negative and you bring it inside one of these factors, either the x plus 5 or the x minus 3, that negative is going to end up getting squared. And we don't want that negative to be squared whatsoever. So let's try not to pull negatives through our factors. Okay? Alrighty. Let's move on to examples 5 and 6. We're dealing with a multiplicity of 3 this time. Notice how we went from a multiplicity of 1 to a multiplicity of 2 in a couple examples. Here's a multiplicity of 3 for examples 5 and 6. And this shows a change in concavity on the x-axis. The graph does not cross the x-axis. This is what we get when we have a little whoop whoop feeling here. Okay, seems to me like I drew some stuff, but I don't see it, so I'm going to go back and draw it again. Okay, so first off, if you have, I'm talking about change in concavity, let's just discuss what concavity is before we go any further. If you have a function like y equals x squared, now I know I don't have an xy axis, and that's fine. This function right here is concave up, because it's like a cup. It can hold liquid. Okay, concave up is like a cup. Concave down would mean all your liquid would fall out, and this is concave down. Well, a change in concavity would be when you're concave up for a portion of the graph and then you're concave down for the other portion of the graph. So let's put this together a little bit here. And let's see, if I just did a concave up and I did a concave down and I let those pieces touch. Now what I want is concave up on one piece and concave down on the other piece, but I need to make this into a function. So what I'm going to do here is I'm going to erase, let's say, the left-hand side of my concave up, and I'm going to erase the right-hand side of my concave down. What I have now is something that looks like example 5, where the function is switching from concave down to concave up. I could do the same thing. Let me do it again. Let's do this concave up business here, concave up. And let's do concave down again. Make sure they touch. Concave down. And this time, instead of erasing the left side of my concave up, I'll erase the right side of my concave up. And instead of erasing the right side of my concave down, I will erase the left side of my concave down. And this gives me, again, a change in concavity. Now, when you go to draw your changes in concavity or your little whoop whoop things, next year in calculus you'll learn that those points are actually called points of inflection. But when you go to draw these changes in concavity, I don't expect you to literally draw a U and an upside down U and then go back and erase. The way we do these is we start with a little horizontal dash. Oh, let's get a marker here. Let's go a little horizontal dash. In both cases, a little horizontal dash. So in this little horizontal dash, I'm going to trace it and then scoop up. I'm going to trace it backwards and then scoop down. And that's how we make our changes in concavity. Same thing to the right. I'm going to trace this and move to the left and scoop up, move to the right and scoop down. And there are examples of changes in concavity. So you will see here that we have a change in concavity right here at x equals 3. We're going concave up here, right? And then to the left of 3, we're going concave down. Everybody see that? So we definitely have a change in concavity at x equals 3. And that's the only root that I have, the only x-intercept, the only 0. So I can go ahead and I can write my function right here. F of x equals, oh, let me talk about it a little bit more before I do that. This function is showing me that we are starting low and ending high. And when we start low and end high, I can tell that I'm dealing with some kind of an odd degree polynomial function because my end behaviors are opposite from each other. So n definitely has to be odd in this case. And because I'm starting low and ending high, just like y equals x cubed, I know that my leading coefficient is going to be positive. Now I can go ahead and write the equation of my graph. I'm going to start off positive, so what I'm going to do is just not put a negative sign. The only root that I have is x equals 3, and if x equals 3 is one of my roots, well then x minus 3 has got to be a factor. And we are talking about a multiplicity of 3, which means I could write this factor out 3 times, or I could just put a cube on there. And that basically gives me the equation of my function. Nothing else I can really do to simplify that, clean that up. It's pretty much done. Okay, moving on to example 6. By the way, n is odd, leading coefficient is positive, so I suppose if I wanted to continue with this, 3 is the only degree I have in this thing. Leading coefficient is positive, so all of this checks. Okay, now moving on to example 6. I'm looking at a polynomial function that's starting high and ending low. And because I can see my far end behaviors are opposites of each other, I know that n is an odd degree polynomial function. The leading coefficient in this case, well, it kind of looks like y equals negative x cubed shifted over a little bit, which is exactly what it's going to end up looking like when I write the equation as well. But my leading coefficient can't be positive in this case. That would be the example 5. My leading coefficient is negative. It's almost like example 5 had some kind of a vertical reflection, and the vertical reflection is what you get by imposing a negative sign on the outside of your function. So leading coefficient is negative. All right, let's go right ahead and start seeing what we can see on this function. Do you notice to the left of negative 2, this function is concave up, and to the right of negative 2, this function is concave down? So we do definitely have a change in concavity. So let's go ahead and write our equation. F of x equals, I have a negative leading coefficient, so I'm going to start off with a negative sign. Negative 2 is my root, or my 0, or my x-intercept. Therefore, x plus 2 has got to be my factor, and I need to see this 3 times. So f of x equals negative quantity x plus 2 cubed. And this, I'm hoping, makes really good sense. As a matter of fact, both of these examples should make super good sense to you, because you should read the transformations from the y equals x cubed graph. On example 5, the only thing that's happening to y equals x cubed is that we have this little minus 3 going on here off the x, which means that y equals x cubed gets moved to the right 3 units, and sure enough, you look at the graph and it did. This over here tells me that y equals x cubed is going to move to the left 2 units, and you look up and it did, and this little minus sign here tells me that I'm going to have a vertical reflection, so y equals x cubed gets reflected over the x-axis, and we sure enough looks just like it. So I think everything is good for those. Let's see, this is odd, matching our word odd up here, leading coefficient being negative, that matches, so we're good to go here. Alrighty. A few more examples, we'll call it a night, eh? Okay, example 7 and 8. What do we see here with our multiplicities? Looks to me like at x equals negative 5, I'm on example 7 by the way, on x equals negative 5 we are looking at a change in concavity. And at x equals 4 with the same example, again we are looking at a change in concavity for both of those roots. So let's go ahead and think about our function a little bit. This function definitely starts high and ends high. So we are looking at n being even. So n is even, just like y equals x squared. As a matter of fact, y equals x squared starts high and ends high. So therefore my leading coefficient for this must also be positive, like positive x squared. I'm going to go ahead and start writing my function. I'm looking at f of x equals, I have a positive leading coefficient, so I could put a plus 1, but I'm not going to. If x equals negative 5 is one of my roots, well then x plus 5 has got to be a factor. And I'm looking at cubing it because I want to have a little whoop-whoop thing going on at negative 5, a little change in concavity. I also want a change in concavity at x equals 4. Therefore, x minus 4 quantity cubed is going to be my other factor. Of course, it's repeating itself 3 times. And that wraps it up. We can't have any other factors in our equation unless we have more intercepts on the x-axis, and this is kind of a simple one because there's only two. So I'm going to say we are done with this. And just double check real quick, like I had a multiplicity of 3 with x equals -5, and I had a multiplicity of 3 with x equals 4. 3 plus 3 makes 6 for the degree of my polynomial function, and the leading coefficient is definitely positive, so yeah, this whole thing checks pretty good. Okay, I got even, positive, everything's checking. Let's move on to example 8. I'm looking at a function here that is starting low and ending high. Do you know an easy polynomial function that starts low and ends high? I do. It's y equals x cubed. So therefore I know that n is odd, just like cube, y equals x cubed. And I also know that my leading coefficient is once again positive. Not negative in this case, positive, because y equals x cubed starts low and ends high also. Alrighty, let's see what we have here. I have a bunch of different roots going on. Let me see. I have f of x is equal to, if I have a positive leading coefficient, of course I could write a plus sign, but I don't need to right here. I'm just going to leave it as positive by not writing anything at all. And I'm going to start with my root of x equals -6, which gives me x plus 6 as a factor. This has a little whoop whoop thing going on right here. You see it, just like at -5 and 4 on the other one. We are concave down, and then we are concave up. So this is a little whoop whoop thing going on at -6. Alrighty, and at x equals 0, we have, ooh, that's weird. We have another little whoop whoop thing going on. So I'm going to say here x minus 0, and I'm going to cube it, and I'm going to go over to the 5. X equals 5 is one of my roots. That means x minus 5. It's got to be a factor, and this is also cubed. Can you see how these have changes in concavity? Here I'm concave up, here I'm concave down. I should do concave down first and then concave up from left to right. My 0 on the left side is concave up, and on the right side is concave down. So you see we have all these changes in concavity going on in all of these problems. I will clean this one up a little bit just because of this piece here. This is x minus 0. So I'm looking at f of x is equal to x cubed times x plus 6 quantity cubed times x minus 5 quantity cubed. And I think I will erase this little thing so that I have room to box my answer without touching anything. Good to go on multiplicities of 1, 2, and 3. Let's see, let's just review those for a quick second here. Multiplicity of 1, we're cutting through, simply cutting through, just intersect or cross the x-axis, no other special behavior. All of these are multiplicity of 1. Here we have multiplicity of 2, which means we have points of tangency. Both examples 3 and 4 have nothing but points of tangency. Multiplicity 2. Here we have multiplicity 3. So I'm dealing with examples 5 and 6 having little whoop whoops. Of course, those are the easiest examples because it only happens once in each graph. And then I move on, I make it happen twice and then 3 times. So we can have lots of different multiplicities, lots of different roots with different multiplicities throughout the problems. Alrighty, I never did check this one, did I? See how nothing looks the same? So I have a 3 here for my multiplicity, and a 3 here for my multiplicity, and a 3 here for my multiplicity. 3 plus 3 plus 3 makes 9. That means my degree is odd. That kind of checks. And I guess maybe I haven't even said this, but if you add your multiplicities up for every single one of your roots, it gives you the degree of your polynomial function. Yeah, that would have been nice to have said earlier, right? Anyway, we have all this. We look through everything here. We have a positive leading coefficient because we're starting low and ending high. Everything checks off okay there. All right, multiplicity of 4. The graph is tangent to the x-axis, but flatter than a multiplicity of 2 at the point of tangency. The graph does not cross the x-axis. So we basically have like a y equals x squared graph that got squished a little bit. And when you get squished a little bit, it flattens out on the bottom. That's pretty much all that's happening. Nothing's bubbling out, but it definitely flattens out. So we have a multiplicity of 4. It's going to be really hard for us to distinguish with our own eyes when we're not at a multiplicity of 2, but we're moved to a multiplicity of 4. It's going to be super hard. I'm not even going to make you accountable for that, but let's just go ahead, and since this is an example problem that we're doing, we will go ahead and write this out anyway. So I am looking at let me see, this function is starting high and ending high, which means that the degree of my polynomial function is what? What do you think? What function do you know starts high and ends high? And I'm hoping that you're saying y equals x squared. So you know that we have an even polynomial function. Also, because the left and right hand behavior are absolutely identical, far end behaviors are identical, they're both high. I'm looking also with a leading coefficient that is greater than 0, just like y equals x squared. So f of x equals, and again, I could start this off with a plus sign, but not putting a plus sign means it's a plus sign, so I'm better off there. X equals -4 is one of my roots. That means x plus 4 has got to be a factor. And I'm looking for a multiplicity of 4 this time. And that's all I have. That's it. We are complete with that problem. Pretty simple. And of course, I told you we were dealing with a multiplicity of 4, so that should make life a little bit easier with these two examples. All right, example 10, I'm looking at starting low and ending low. That means that again, n is even because the far end behavior matches on the left side and on the right side. As x approaches negative infinity and positive infinity, the y's are doing the same thing. That's what constitutes an even behavior. And my leading coefficient this time is not going to be positive like y equals x squared, but it looks like y equals x squared got flipped upside down or reflected over the x-axis. So that only occurs when we have a negative leading coefficient. Alrighty, start this thing off. F of x equals, here's my negative leading coefficient. My first root that I have is -1, which means x plus 1 is going to be a factor. And I'm going for a multiplicity of 4, which is how many times the factor occurs as well. So put a 4 up there. And then when x equals 5 is a root, I get x minus 5, again with a multiplicity of 4. So I'm hoping to you these look a little bit wider than y equals x squared. They do to me, so let's hope. We're good with both those, and these are so simple that, you know, there's really not much to do to check this thing. We got 4 here and 4 here makes 8, so yeah, we're even. Negative leading coefficient, didn't forget it, we're all good there. Positive leading coefficient on number 9, that's what that says. Even degree polynomial function, that's all good. Both of these check out really nice. Alright, let's move on to a multiplicity of 5. See, this is where I talked about concave up and concave down. You know what? We can just go ahead and erase that, right? I must be on a really small erase marker. So let's get bigger and get that out of there because we already did this up above. Okay. So I'm looking at this function right here. It's starting high, ending low. That tells me I'm dealing with a degree that's odd. Degree is odd. Even degree polynomial functions, let's not forget, even degree start and end in the same direction. Odd degree are opposite directions. So n is odd, just like y equals x cubed. However, y equals x cubed starts low and ends high. I want something to start high and end low, so that would be like y equals negative x cubed. My leading coefficient, therefore, must be negative. All right, I only have one root, and it's a multiplicity of 5 because these are the examples for multiplicity of 5. Let's look at this thing. The graph shows a change in concavity on the x-axis, but flatter than a multiplicity of 3. So I'm hoping this makes really good sense to you. These things almost look as if they flatten out quite a bit. Matter of fact, if I were looking at this graph, I might even guess this to be something other than a multiplicity of 5, even flatter than a 5, but we'll go for it since I did draw it for this example. All right, so I'm looking at f of x equals 2 is my root, so x minus, what did I forget? Tell me. Leading coefficient is negative. I need a negative sign right here. And now x minus 2, quantity to the 5th. And that's all I can do. There's only one root, so I only have one factor, and I'm finished. And it's pretty simple. It looks to me like I have an odd exponent right here. It takes care of this odd degree polynomial function. I didn't forget my negative sign. It's right there. Yep, So that all checks off. Let's go over here. I am looking at a function starting low and ending low. It tells me that n in this case has to be even. However, y equals x squared is an even function, but that starts high and ends high. This starts low and ends low, and therefore my leading coefficient must be negative. Alrighty, let's start our function. F of x equals, let's get that negative out of the way again. Negative, let me see, -3. If x equals -3 is a root, then x plus 3 has got to be a factor, and the multiplicity is a 5 for this example. And then if x equals 4 is a root, then x minus 4, quantity to the 5th, is going to be the other factor. There's really nothing I can do to simplify that either. I'm going to go ahead and box that as my final answer. I will, of course, look here and say 5 and 5 make 10. 10 is even, so that checks off. I've got a negative leading coefficient right here. Leading coefficient's negative. I did everything I was supposed to do. Alrighty, don't forget to check that negative sign because even I leave it off once in a while. Alright, multiplicity of 6. The graph is tangent to the x-axis but flatter than a multiplicity of 4 at the point of tangency. The graph does not cross the x-axis. So just like multiplicity of 2 and multiplicity of 4, we have a point of tangency and the graph does not cross the x-axis. It just gets flatter and flatter and flatter. Multiplicity of 7. The graph shows a change in concavity on the x-axis but flatter than a multiplicity of 5. And then when you go to multiplicity of 8, the graph is tangent to the x-axis but is flatter than a multiplicity of 6 at the point of tangency. And again, the graph does not cross the x-axis. Look at this. We have a point of tangency here and a point of tangency here twice. And this is for multiplicity of 6, multiplicity of 8. We also had a point of tangency with a multiplicity of 4. We also have a point of tangency with a multiplicity of 2. So yeah, you guessed it, 2, 4, 6, 8, 10, 12, 14, 16, 18, ... Any even multiplicity will have a point of tangency at that particular root. And for the odds, it's kind of split a little bit. Multiplicity of 7 is definitely showing a change in concavity, just like multiplicity of 9 shows a change in concavity. They just get flatter and flatter and flatter the higher the multiplicity is. All right, so this maintains itself and you have a vicious cycle bouncing back and forth between having a point of tangency and having a point of concavity change, which is, like I said before, what we call an inflection point in calculus. Alrighty, let's keep on. I made you a little chart here. Let's see, multiplicity of the root. There we go, all the different multiplicities, 1, 2, 3, 4, 5, 6, 7, 8, 9, ... The behavior of the graph at the root on the x-axis. So 1 is the only one that's really super basic right here. Cuts right through, has no basic, well, has no difficulties whatsoever. It is basic. It doesn't have any special properties. It just goes right through really fast. The points of tangency and the changes in concavity, which are our points of, what do we say? Inflection. You get that little whoop whoop thing on the 3, 5, 7, 9, and so be it. We have to know the multiplicity of the roots. We've got to be able to recognize the multiplicity within a function, within the functional notation, and within the graph itself.